Hierarchical transformers for long document classification. BERT, which stands for Bidirectional Encoder Representations from Transformers, is a recently introduced language representation model based upon the transfer learning paradigm. We extend its fine-tuning procedure to address one of its major limitations: applicability to inputs longer than a few hundred words, such as transcripts of human call conversations. Our method is conceptually simple. We segment the input into smaller chunks and feed each of them into the base model. Then, we propagate each output through a single recurrent layer, or another transformer, followed by a softmax activation. We obtain the final classification decision after the last segment has been consumed. We show that both BERT extensions are quick to fine-tune and converge after as little as one epoch of training on a small, domain-specific data set. We successfully applied them in 3 different tasks involving customer call satisfaction prediction and topic classification, and obtain a significant improvement over the baseline models in 2 of them. Bidirectional encoder representations from Transformers. BERT is a novel Transformer 1 model which recently achieved state-of-the-art performance in several language understanding tasks, such as question answering, natural language inference, semantic similarity, sentiment analysis, and others too. While well suited to dealing with relatively short sequences, Transformers suffer from a major issue that hinders their applicability in classification of long sequences, i.e. they are able to consume only a limited context of symbols as their input. 3. There are several natural language (NLP) processing tasks that involve such long sequences. Of particular interest are topic identification of spoken conversations 4, 5, 6, and call center customer satisfaction prediction 7, 8, 9, 10. Call center conversations, while usually quite short and to the point, often involve agents trying to solve very complex issues that the customers experience, resulting in some calls taking even an hour or more. For speech analytics purposes, these calls are typically transcribed using an automatic speech recognition (ASR) system and processed in textual representations further down the NLP pipeline. These transcripts sometimes exceed the length of 5,000 words. Furthermore, temporal information might play an important role in tasks like CSAT. For example, a customer may be angry at the beginning of the call, but after her issue is resolved, she would be very satisfied with the way it was handled. Therefore, simple bag-of-words models, or any model that does not include temporal dependencies between the inputs, may not be well suited to handle this category of tasks. This motivates us to employ models such as BERT in this task. In this paper, we propose a method that builds upon BERT's architecture. We split the input text sequence into shorter segments in order to obtain a representation for each of them using BERT. Then, we use either a recurrent LSTM11 network or another transformer to perform the actual classification. We call these techniques recurrence over BERT-Robert and transformer over BERT-Tobert. Given that these models introduce a hierarchy of representations, segment-wise and document-wise, we refer to them as hierarchical transformers. To the best of our knowledge, no attempt has been done before to use the transformer architecture for classification of such long sequences. Our novel contributions are 2 extensions, Robert and Tobert, to the BERT model. which enable its application in classification of long texts by performing segmentation and using another layer on top of the segment representations. State-of-the-art results on the Fisher topic classification task. Significant improvement on the CSAT prediction task over the MSCNN model. Related work. Several dimensionality reduction algorithms such as RBM autoencoders, subspace multinomial models (SMM) are used to obtain a low-dimensional representation of documents from a simple bow representation and then classify it using a simple linear classifiers 12, 13, 14. 5. In 15, hierarchical attention networks are used for document classification. They evaluate their model on several datasets with average number of words around 150. Character-level CNN are explored in 16, but it is prohibitive for very long documents. In 17, dataset collected from archive papers is used for classification. For classification, they sample random blocks of words and use them together for classification instead of using full document, which may work well as archive papers are usually coherent and well written on a well-defined topic. Their method may not work well on spoken conversations as random block of words usually do not represent topic of full conversation. Several researchers address the problem of predicting customer satisfaction. 7, 8, 9, 10. In most of these works, logistic regression (SVM), CNN are applied on different kinds of representations. In 18, authors use BERT for document classification, but the average document length is less than BERT maximum length 512. Transformer XL3 is an extension to the transformer architecture that allows it to better deal with long inputs for the language modeling task. It relies on the auto-regressive property of the model, which is not the case in our tasks. Method 3.1. BERT. Because our work builds heavily upon BERT, we provide a brief summary of its features. BERT is built upon the transformer architecture, 1, which uses self-attention, feed-forward layers, residual connections, and layer normalization as the main building blocks. It has 2 pre-training objectives. Masked language modeling. Some of the words in a sentence are being masked and the model has to predict them based on the context. Note the difference from the typical auto-regressive language model training objective. Next sentence prediction. Given 2 input sequences, decide whether the second one is the next sentence or not. BERT has been shown to beat the state-of-the-art performance on 11 tasks with no modifications to the model architecture, besides adding a task-specific output layer 2. We follow same procedure suggested in 2 for our tasks. Fig. 1 shows the BERT model for classification. We obtain 2. kinds of representation from BERT: pooled output from last transformer block, denoted by H, and posterior probabilities, denoted by P. There are two variants of BERT: BERT base and BERT large. In this work we are using BERT base for faster training and experimentation. However, our methods are applicable to BERT large as well. BERT base and BERT large are different in model parameters, such as number of transformer blocks, number of self-attention heads. Total number of parameters in BERT base are 110M and 340M in BERT large. BERT suffers from major limitations in terms of handling long sequences. Firstly, the self-attention layer has a quadratic complexity O, n2, in terms of the sequence length n1. Secondly, BERT uses a learned positional embedding scheme too, which means that it won't likely be able to generalize to positions beyond those seen in the training data. To investigate the effect of fine-tuning BERT on task performance, we use either the pre-trained BERT weights 1 or the weights from a BERT fine-tuned on the task-specific dataset on a segment level, i.e., we preserve the original label but fine-tune on each segment separately instead of on the whole text sequence. We compare these results to using the fine-tuned segment-level BERT predictions directly as inputs to the next layer. (3.2) Recurrence over BERT. Given that BERT is limited to a particular input length, we split the input sequence into segments of a fixed size with overlap. For each of these segments, we obtain HRP from BERT model. We then stack these segment-level representations into a sequence, which serves as input to a small, 100-dimensional LSTM layer. Its output serves as a document embedding. Finally, we use two fully connected (3.3) Transformer over BERT. Given that transformers edge over recurrent networks as their ability to effectively capture long-distance relationships between words in a sequence 1, we experiment with replacing the LSTM recurrent layer in favor of a small transformer model, 2 layers of transformer building block containing self-attention, fully connected, etc. to investigate if preserving the information about the input sequence order is important. We also build a variant of TOBERT which learns positional embeddings at the segment-level representations, but is limited to sequences of length seen during the training. TOBERT's computational complexity O, N2K2, is asymptotically inferior to ROBERT, as the top-level transformer model again suffers from quadratic complexity in the number of segments. However, in practice this number is much smaller than the input sequence length nk less than n, so we haven't observed performance or memory issues with our datasets. (4) Experiments. We evaluated our models on 3 different datasets: CSAT dataset for CSAT prediction, consisting of spoken transcripts, automatic VSR, 20 newsgroups for topic identification task, consisting of written text, Fisher Phase 1 corpus for topic identification task, consisting of spoken transcripts, manual, 4.1. CSAT dataset consists of U.S. English telephone speech from call centers. For each call in this dataset, customers participated in that call gave rating on his experience with agent. Originally, this dataset has labeled rated on a scale 1 to 9, with 9 being extremely satisfied and 1 being extremely dissatisfied. Fig. 2 shows the histogram of ratings for our dataset, as the distribution is skewed towards extremes. We choose to do binary classification with ratings above 4.5 as satisfied and below 4.5 as dissatisfied. Quantization of ratings also helped us to create a balanced dataset. This dataset contains 4,331 calls, and we split them into 3 sets for our experiments: 2,866 calls for training, 362 calls for validation, and finally, 1,103 calls for testing. We obtained the transcripts by employing an OSR system. The OSR system uses TDNN-LSTM acoustic model trained on Fisher and switchboard datasets with lattice-free maximum mutual information criterion 19. The word error rates using 4-gram language models were 9.2% and 17.3% respectively on switchboard and call home portions of a VAL 2000 dataset too. (4.2) 20 newsgroups. 20 newsgroups 3 dataset is one of the frequently used datasets in the text processing community for text classification and text clustering. This dataset contains approximately 20,000 English documents from 20 topics to be identified, with 11,314 documents for training and 7,532 for testing. In this work, we used only 90% of documents for training and the remaining 10% for validation. For fair comparison with other publications, we used 53,160 words vocabulary set available in the dataset's website. (4.3) Fisher Phase 1 U.S. English corpus is often used for automatic speech recognition in speech community. In this work, we used it for topic identification as in 4. The documents are 10-minute-long telephone conversations between 2 people discussing a given topic. We used same training and test splits as 4, in which 1374 and 1372 documents are used for training and testing respectively. For validation of our model, we used 10% of training dataset and the remaining 90% was used for actual model training. The number of topics in this dataset is 40. (4.4) Dataset Statistics. Table 1 shows statistics of our datasets. It can be observed that average length of Fisher is much higher than 20 newsgroups and CSAT. Cumulative distribution of document lengths for each dataset is shown in Fig. 3. It can be observed that almost all of the documents in Fisher dataset have length more than 1,000 words. For CSAT, more than 50% of the documents have length greater than 500, and for 20 newsgroups only 10% of the documents have length greater than 500. Note that, for CSAT and 20 newsgroups, there are few documents with length more than 5,000. (4.5) Architecture and training details. In this work, we split document into segments of 200 tokens with a shift of 50 tokens to extract features from BERT model. For Robert, LSTM model is trained to minimize cross-entropy loss with Atom Optimizer 20. The initial learning rate is set to 0.001 and is reduced by a factor of 0.95 if validation loss does not decrease for 3 epochs. For Tobert, The transformer is trained with a default BERT version of Atom Optimizer 2 with an initial learning rate of 5e-5. We report accuracy in all of our experiments. We chose a model with the best validation accuracy to calculate accuracy on the test set. To accommodate for non-determinism of some TensorFlow 4 GPU operations, we report accuracy averaged over 5 runs. Results table. To present results using pre-trained BERT features. We extracted features from the pooled output of final transformer block as these were shown to be working well for most of the tasks too. The features extracted from a pre-trained BERT model without any fine-tuning lead to a subpar performance. However, we also noticed that TOBERT model exploited the pre-trained BERT features better than RAWBERT. It also converged faster than RAWBERT. Table 3 shows results using features extracted after fine-tuning BERT model with our datasets. Significant improvements can be observed compared to using pre-trained BERT features. Also, it can be noticed that TOBERT outperforms RAWBERT on Fisher and 20 newsgroups dataset by 13.63% and 0.81% respectively. On CSAT, TOBERT performs slightly worse than RAWBERT, but it is not statistically significant as this dataset is small. Table 4 presents results using fine-tuned BERT predictions instead of the pooled output from final transformer block. For each document, having obtained segment-wise predictions, we can obtain final prediction for the whole document in 3 ways. Compute the average of all segment-wise predictions. And find the most probable class. Find the most frequently predicted class. Train a classification model. It can be observed from Table 4 that a simple averaging operation or taking most frequent predicted class works competitively for CSAT and 20 newsgroups but not for the Fisher dataset. We believe the improvements from using RAWBERT or TOBERT compared to simple averaging or most frequent operations are proportional to the fraction of long documents in the dataset. CSAT and 20 newsgroups have, on average, significantly shorter documents than Fisher, as seen in Fig. 3. Also, significant improvements for Fisher could be because of less confident predictions from BERT model, as this dataset has 40 classes. Fig. 4 presents the comparison of average voting and TOBERT for various document length ranges for Fisher dataset. We used fine-tuned BERT segment-level predictions (P) for this analysis. It can be observed that TOBERT outperforms average voting in every interval. To the best of our knowledge, this is a state-of-the-art result reported on the Fisher dataset. Table 5 presents the effect of position embeddings on the model performance. It can be observed that position embeddings did not significantly affect the model performance for Fisher and 20 newsgroups, but they helped slightly in CSAT. Prediction: an absolute improvement of 0.64% F1 score. We think that this is explained by the fact that Fisher and 20 newsgroups are topic identification tasks, and the topic does not change much throughout these documents. However, CSAT may vary during the call, and in some cases a naive assumption that the sequential nature of the transcripts is irrelevant may lead to wrong conclusions. Table 6 compares our results with previous works. It can be seen that our model Tobert outperforms CNN-based experiments by significant margin on CSAT and Fisher datasets. For CSAT dataset, we use multi-scale CNN, MSCNN, as the baseline. Given its strong results on Fisher and 20 newsgroups, the setup was replicated from 6 for comparison. We also see that our result on 20 newsgroups is 0.6% worse than